Okay, this is the extra practice problems for chapter 14. Number 1. Using the bond energy table on page 420, determine the enthalpy of the following reaction. Okay, so there's the reaction that we're going to figure out the enthalpy for. And we're going to use the bond energies on page 420. And so you know that's going to be using the Lewis structures. So first we have to draw the Lewis structures. And each of these has 1, so they will connect that way. This is 2 oxygens. This is 1 CO2 plus 2 H2Os. There are your bonds that you're actually going to do. Now, when we're using the Lewis structures, we are actually going to work from left to right. It's the only place in the chapter that we will. We have 1, 2, 3, 4 of these bonds. So we have 4 moles of a C to H bond, or an H to C bond. And that is 410. And this is kilojoules per mole. Plus, we have 2 double bond O's. So I'm going to put 2 moles. And on the table, that is 498 kilojoules per mole. Minus, we have 2 C double bond O's. I'm going to move this water up a little so it's out of our way. Okay, we have 2 C double bond O's, and so that is 732 kilojoules per mole minus, and I have 2 moles, but there's 2 bonds in each mole, so I have 2 moles times 2, and that is the HO, which is 460 kilojoules per mole. Okay, now that is where you start. And then I want you to look here. This goes to the tens place. This goes to the ones, the 10s. So our answer has to go to the tens place. So when you do this, when I do all of this, I get this out of my calculator. But I already told you this goes to the tens place and this goes to the tens place. So my answer has to go to the tens place. So we're not going to leave it like this. We're going to make it negative 670 kilojoules. Because we have to go to this, so we look at this, this rolls this up, and so that would be our answer. And so that is a negative enthalpy, therefore it's an exothermic reaction, so we could actually add this here to the product side. You did not have to do that. I'm just doing it because that's where it belongs. So, number 2, the enthalpy of the following reaction is negative 280 kilojoules per mole. What is the energy of the triple bond between carbons? So that's what we're looking for. So, okay, we're on number 2. And we're supposed to figure out the enthalpy of the triple bond C in here. And we're using our bond energies on table 420 again. So we're going to work from left to right. So we're going to have 2 times, we're going to have 2 moles of the H to C bond, which is 410 kilojoules per mole. And then plus 1 mole of the C triple bond C, and that's going to be in kilojoules per mole is what we're trying to find here. Plus we have 2 moles of the H to H, which is 436 kilojoules per mole, minus we have 1, 2, 3, 4, 5, 6 moles of the H to C, which is 410 kilojoules per mole. And then we have 1 of these minus 1 mole of the C to C, which is 350. And this whole thing equals a negative 280 kilojoules per mole is what we're told. And so actually when we write it in here, we just write it that way. Okay, so when we do this, that's what we're solving for. So when I do these, now the trick is this. When I added these up, notice it's to the tens place, that's the ones place, but this is the tens place. So this should have been to the tens place. And that's the proper number of significant figures. And I am going to solve for this. So I'm going to add the 280 to this side. And I'm going to subtract. Oh, that's going to give me a negative, isn't it? That side. So then whatever this is, I'm going to multiply it by a negative 20. Okay, so what I get here is negative 840 kilojoules, but now I'm going to multiply through by negative so that this is, the bond is positive. So that's going to give me 840 kilojoules, and that's what the triple bond C equals, is 840 kilojoules. So there's our answer. So we just made this our variable. We plugged everything else in, try to work carefully, and watch your significant figures, and that's how we got that answer. Remember, when you're using the Lewis structures, you have to work from left to right. So you figure out the bond energies of the reactants and then subtract the bond energies of the products. And only when you're using the Lewis structures are you going to do that. Otherwise, you're going to do it the other way and go products minus reactants. Number 3. What is the enthalpy for the complete combustion of CH4O liquid at 25 degrees? Use Hess's law. So we're going to completely combust CH4O liquid. CH4O liquid. You have memorized how to do a complete combustion reaction. We're going to add oxygen gas. You're going to produce carbon dioxide gas and water vapor. Let's balance this bad boy. Notice that I have one of these. I have 4 of these, so I'm going to need 2 of these just to balance the hydrogens. But look what I've got here. I've got even numbers of oxygens over here, but an odd number over here. So I'm going to want to even this up. So I'm going to put a 2 out here. That gives me 2 of these, so 2 of these. That gives me 8 of those, so I'm going to make this a 4, so I have 8 hydrogens. Okay, now let's deal with the oxygen. We have 4 plus 4 is 8. I have 2 here, so I want to make this look like a 6, and that will give me my 8. So I have 2 carbons, 8 hydrogens, 8 hydrogens. I have 2 times 2 is 4, plus 4 is 8 oxygens. I have 2 oxygens here, and 6 here is 8. So just balancing it is a little bit of a challenge. Okay, then we're going to use Hess's law. Now remember, now we're doing the products minus the reactants. So first we're going to do 2 moles, and we look on the Hess's law chart, which is on page 424. And we have 2 moles of CO2 gas. Make sure you look for it in the gas form, just in case, because those are on here. Negative 393.5. Negative 393.5 kilojoules per mole. Keep your dimensions with you. Okay, so we get the 2 moles of that, plus 4 moles of water vapor. So we're going to look at our chart. We're going to find water vapor, negative 241.8, negative 241.8 kilojoules per mole, minus, because now we're on the reactant side, we have 2 moles of CH4O, and that is a liquid, so it's on our chart, negative 238.7. And then this is in its elemental state, so it's going to zero out. So I'm going to put here negative 0. Okay? So now we can go about trying to figure it out. Watch your significant figures. This is negative. Watch your signs as well as your significant figures. This is actually negative, isn't it? Because it's positive times a negative. Okay, minus a negative is plus a positive. I get negative 1,276.8. Now please notice all of these go to the tenths place, and you're adding or subtracting. That is a negative. I don't know if you can see it. So your answer has to go to the tenths place. You can see where you could really easily mess up the significant figures, or you can mess up these signs. Make sure you watch these signs, because that'll mess you all up if you're not careful. And that's one I have problems with, is watching the signs. Let's see, number 4. The enthalpy for the following reaction is negative 902.0 kilojoules at 25 degrees. What is the enthalpy of formation of nitrogen monoxide? And actually, we're told that the whole reaction is negative 902. So we're going to add that over here. Excuse me, not 902, 920. No, it is 902. 902.0 kilojoules. So we're given that information. Okay, and we are asked to find this one. That's what we're looking for, is the kilojoules of what is the enthalpy of formation of that. So we're going to use the chart on page 424, and we are going to work from this side minus this side. So first we're going to start with that. We have 4 moles of what we're looking for, and that would be kilojoules per mole. That's what we're looking for. Okay, plus 6 moles of water vapor, which water vapor is negative 241.8 kilojoules per mole. Okay, we're not going to deal with that right now. Minus, now we're going to go 4 moles, we're back over to the reactant side, of ammonia gas, and be careful because there's an aqueous one there, so don't grab that by accident, because your numbers will be wrong. Okay, so there's the ammonia gas. Good. And this is an element, so it's going to be 0. And this whole thing equals negative 902.0 kilojoules. And we know that because we were given that. Okay, so using that information, we're going to have 4 times whatever NO is in kilojoules, plus, that's a minus actually because that's a negative, so it's going to be minus okay, this goes out to the tenths place, so I'm going to take it out to the tenths place. plus, because I have a negative and a negative, okay, so now we're going to get this on one side and everything else on the other side. So I'm going to put in my 902 negative minus 183.6, so I just subtracted that from both sides, plus 1450.8. So that is 4 NO kilojoules equals 365.2 kilojoules. And where did I get that? I just took this and added this to both sides, so that got rid of this. And I said, excuse me, I subtracted that from that side and I added this to that side, and this is what I got. So far I've just shifted the numbers over there. Now I'm going to divide both sides by 4. Which is 91.3 kilojoules. And so the NO has 91.3 kilojoules per mole of NO. That's how we figured it out. So we just left that to be what we're looking for, but we just plugged it in with everything else we know, and then we just solve carefully. Number 5, how much energy is released when 4.5 kilograms of CH4O liquid undergoes complete combustion? And we already figured out note that the enthalpy of that reaction is in problem number 3. So we already did the complete combustion reaction in problem number 3. So we're going to go ahead and use that information. So here I've just done the complete combustion reaction again, and I've put in there the enthalpy of this combustion reaction that we calculated in number 3. It was a negative 1276.8 kilojoules, so I've added it as a product because it's an exothermic reaction. Now in number 5, we are told how much energy is released when 4.5 kilograms 4.5 kilograms, which is the same thing as 4.5 times 10 to the third grams of this is burnt, combusted. How much energy are we going to get? So we're going to have to go through the mole tunnel as usual. We're going to go from there to there because that's where the energy is. And whoops, we're going to find out how many moles of this we have. Okay, every 1 mole of this, we have 4.04 plus 12.01 plus 16. And so this is 32.05. 4 significant figures, 2 significant figures. My answer that comes out of my calculator is 140.4. So I'm going to put 140. And that is moles of CH4O. That's in 2 significant figures, so that's what I needed. So now I'm to the moles of this, and I want to go over to there. So I'm going to, you know what, I'll just rewrite it. 140 moles of CH4O times line. We have moles of CH4O, and then this is going to be our energy up here because that's what we're trying to go through. And so how we find what goes here is just like any other stoichiometry. You're going to go up to your balanced chemical equation. There's a 2 here, so there has to be a 2 here. Okay, so now that you have that, now what comes out of my calculator is 89,376 kilojoules. But this is in 2 significant figures, so my answer has to be in 2 significant figures. That's going to roll down. So it's just going to be 89,000 kilojoules. And that would be your correct answer because it's got the correct number of significant figures. Not that hard. Just doing stoichiometry, finding out how many moles, going through the mole tunnel. And this time when you go through the mole tunnel, as always, whatever's here has to go down here. But now you're trying to get to the energy, so you're putting the energy up there. And then you're going to put in whatever the stoichiometric coefficient is into this. Because for every 2 moles of this, that's how much energy you get. For every 3 moles of oxygen, that's how much energy you get. For every 2 CO2s, you're producing that amount of energy with it. Given the reaction coordinate diagrams below, and we have 1 and 2, A, which represents an endothermic reaction. Okay, well, remember with an endothermic reaction, it's going to start someplace and then end higher. Because then when you take this number minus this number, it's going to be positive, which would be endothermic. So which one looks like that? That would be reaction number 2. And then B says, what is the enthalpy of reaction 1? Well, with reaction 1, it goes like this. You're going to look at this number over here, which is 200, minus this number over here, which is 300. So 200 kilojoules minus 300 kilojoules is a negative 100 kilojoules would be the enthalpy for reaction 1. What is the enthalpy for reaction 2? Here you have it going like this and then going up. You know, it's above here to here. So over here, it's at 250 minus over here, which is at 150. So that's going to give you 100 kilojoules, but this time it's positive because it's an endothermic reaction. Remember on this one, when you went over to the far right, this was 200 kilojoules, and this one was 300 kilojoules. So when you subtract, you say 200 minus 300, that gives you the negative. And then D, which reaction has the highest activation energy? Now remember, the activation energy is whatever this is minus this, the top of this peak. Well, this one goes to, I would say, 575 minus 300. That is my estimation. Which is going to be about 275 kilojoules for that activation energy. This one over here goes up to, oh, I don't know, let's say 350. It's really just below that, so we'll go 340 kilojoules minus 150 kilojoules, which is basically 190 kilojoules. So obviously this one has the highest activation energy, so reaction 1 has the highest activation energy there. And you could estimate. Don't freak out about estimating, okay? Go over to number 7, please. Number 7, determine the sign of entropy for the following reactions. Okay, the first on A, we go from gases to a solid. And so are we increasing or decreasing entropy as we go this way? This has more entropy, this has less entropy, and therefore we are decreasing entropy. So our entropy is going to be negative here because it's decreasing. On the next one, we go from solids to a gas. So now we're increasing entropy, and so this one would be a positive sign. The last one, we have all gases. We have gases here going to gases here. So we go to look at something else. We have 2 moles plus 3 moles is 5 moles of gas here. And on the product side, we have 4 moles of gas. Therefore, this is more entropy than this one because there's more actual molecules than there are here. Therefore, this one would be negative because the entropy would be decreasing as it goes across. So in other words, you're looking, is the entropy increasing? No, here it's decreasing, so it's negative. Here it's increasing, so it's positive. Here it's decreasing, so it's negative. Number 8, in problem 3, you calculated the enthalpy for the complete combustion of CH4O liquid at 25 degrees. Determine the entropy for the same reaction. On this one, we're going to use the chart on the page 437, the bottom of 437, and we are using the combustion. So we are doing delta S, and that is going to be the summation of the products, 2 moles, and then we're going to look on the chart for carbon dioxide gas, CO2 gas, and it's 213.7. This is joules per mole Kelvin. Be careful, not kilojoules. Okay, now we've got plus 4 moles of water, and this is water vapor, so we look on our chart and it's 188.7. 188.7. This is joules per mole Kelvin. And then we're going to subtract 2 moles of this CH4O, and we've got the liquid, so that is 126.8 joules per mole Kelvin, minus 3 moles, and in this case, even the elements have entropies, 205. This is times 205.0 joules per mole Kelvin. Making sure it's 205.0. Yes, it is. Okay, so there we've got all of our numbers. Okay, and then this goes to the tenths place. So this one should go to the tenths place also. There we go. And my answer is 313.6 joules per Kelvin. There you go. So it's just the summation of the entropies of the products minus the summation of the entropies of the reactants. Notice your answer is in joules per Kelvin because you didn't have anything to cancel that out. Number 9, use the Hess's law technique to calculate the delta G of the complete combustion of C2H6 at 25 degrees. Okay, when I do this, I balance that, I balance this, and then I end up with 7 oxygens. I did 7 over 2, and then I'm going to multiply through by 2. 2, 7, 4, 6. Let's check it. 12, 12, 4, 4, 8 plus 6 is 14, 14. Okay, so we're balanced there, and uses Hess's law to calculate delta G. And to use Hess's law to calculate delta G, that means we're going to use the chart on page 444. And so we're going to say delta G equals 4 moles, and the CO2 gas on this chart is negative 394.4, and this is kilojoules per mole. So entropy is the only one that's real different. Plus 6 moles of gaseous water, which is negative 228.6 kilojoules per mole, minus 2 moles of C2H6 gas, negative 32.9 kilojoules per mole. And the last one is 7 moles of O2, which is not on there because the elements zero out again. Yay! So that's a 0. Okay, so then we do this. Okay, so that's how you would find, using Hess's law, you would find your Gibbs free. There it is. These go to the tenths place, and so your answer would have to be to the tenths place. Last one, number 10. Enthalpy and entropy of several reactions are given below. For each reaction, determine whether it's spontaneous at all temperatures, never spontaneous, no matter what temperature, or spontaneous for a range of temperatures. If it's spontaneous for a range of temperatures, give the range. Okay, remember that we learned in class, and I went over this with you in class, that if the delta H is negative and the delta S is positive, it is a negative delta G, and therefore it is spontaneous. If we have the delta H is positive and the delta S is negative, you have a positive delta G, therefore not spontaneous, always. And then if they have the same sign, it depends on the temperature, and you're going to have to figure it out. These two have the same sign. then you're going to have to figure it out. So let's look at the first one. We have the same sign, and therefore we have to figure it out. On the second one, we have a positive and a negative, so that one, B, is never spontaneous. Never spontaneous. The next one, you have the same sign, so we're going to have to calculate it. And for D, you have a negative enthalpy and a positive entropy. Therefore, D is always spontaneous. Always spontaneous. So A and C are the two that we actually have to do the calculations on. So on A, we are going to use enthalpy minus T times the entropy. Okay, so let's do that for A. So for A, we have negative 115.6 kilojoules minus, we're going to figure out the T, and then we have a negative entropy, so we're going to make this whole thing a positive, and it's going to be 117.2 joules per Kelvin. So this has to go to joules. So let's make that negative 115.6 times 10 to the third joules plus T times 117.2 joules per Kelvin. Okay, and we know we want to make this spontaneous, and to be spontaneous it would have to be a negative number, so we're going to make this whole thing less than 0. Okay, that way we're going to make it spontaneous. So now we're solving for T, and that's what we're doing. So if we multiply the, we have to subtract that, don't we? So we subtract that over to here. No, we want to subtract that. We want to leave that alone. Add this to both sides. So we add this to both sides. We've got so we're going to divide both sides by that, and this gives me a temperature of 986.3 Kelvin. Okay, so I just plugged in what we were given. We made it so it would be spontaneous, so it would have to be negative, and then we just solved for T. And that's how we got our answer, 4 significant figures. So we have 4 significant figures in our answer. Let's do the other one that we had to figure it out on, which was on C. And so here we want it to be spontaneous again, so we're going to make this whole thing less than 0. The delta H for this one is 203.1 kilojoules. So once again, we're going to have to make that joules, so we're going to take that whole thing and go times 10 to the third joules minus the temperature. And then the entropy for that is 132.6 joules per Kelvin. So once again, you're just going to solve for this. So if we add this to both sides this time, we get the temperature, and that's 132.6 joules per Kelvin. It's less than 203.1 times 10 to the third joules. So now we're going to divide this, and that's going to give me a temperature greater than 3 significant figures, 4 here, 15.32 Kelvin. And so that's how you would 1532 Kelvin. Let me just check that. Yep. So there it is. And that's when it would be spontaneous, because that's when it would be Gibbs-free that's less than 0. Okay. So finish studying for this, take your test, read the first half of the next chapter, and have a very blessed week.